Well, yesterday we were talking about vector fields on a manifold. So, throughout, as I told you earlier also, okay, M will be the symbol for a manifold of dimension n. Manifold, a C infinity manifold rather, of dimension n. So, we were talking about vector fields on M, and we defined them as an object which are in fact maps which assign to each point P a tangent vector. Such an object is called as vector field. I discussed some examples also. And the local expression, if you are working in a coordinate neighborhood uxi, so on uxi, the expression for the vector field comes out to be some function xi I into del upon del xi. Summation over I is there. It runs from 1 to n, where xi i's are functions. Xi ix are real valued functions, are real valued C infinity functions. So, this is a vector field, and you can see from here that if I restrict a vector field to a point P, the right side will become xi I at the point P, means it is a scalar, into del upon del xi at P. So, these are basic tangent vectors multiplied by these scalars will remain a tangent vector. So, xp becomes a tangent vector, therefore, this is a expression, local expression of the vector field x. Now, from here we also realized, because of the property of del upon del xi, that vector field can also be regarded as a map from the space of differentiable functions on M to C infinity M itself. And moreover, it will have the properties like linearity. So, x of f plus g will be equal to xf plus xg, and x of number 2, x of alpha f is equal to alpha times xf. So, it satisfies Leibniz property, and number 2, it satisfies the Leibniz property. The first one is linearity, the second is the Leibniz property. This is equal to xf into g plus f times x into g. Into g means operating on g. So, for every real valued function f on M, xf once again is a real valued function on M. It satisfies the two characterizing properties. Okay, so, these are some of the things which I discussed about vector fields in my last lecture. Now, there is another thing. If you are looking vector field locally, suppose there are two coordinate neighborhoods, one is uxi and the other is v x dash I. Okay. And these coordinates neighborhood overlap each other smoothly. So, there is an intersection between the two neighborhoods, and the expression of the vector field x in uxi suppose is something xi I del upon del xi. And the same vector field, suppose I am working over here in the overlapping part, the same vector field will also have an expression some xi dash I or j del upon del x dash j. So, the vector field has two different expressions. So, we expect that these components of the vector field must be related to each other. So what will be the relation? We can easily work it out. So what I will do, I will write down xi dash j del upon delta x dash j. This I can write down as, now both of them are x, so they are all equal. Okay. Now this I can write down as xi dash j into, now look here, for example, if I am differentiating f with respect to x dash j, I can write it down as del f upon del xi into del xi upon delta x dash j. We know this property of the partial derivatives. It's in fact a chain rule, and this is true with coordinate xi also. We have seen this chain rule only in Rn, but since partial derivatives are defined in terms of the partial derivative of Rn, so the same relation will hold over there also. So I will make use of this fact. So xi dash j into del upon del xj, if I remove f from both sides, it will look like this. Okay. So del upon del x dash j I can replace by this quantity. So it will be del xi upon del x dash j into del upon del xi. Okay.
Chain rule always exist in function of compositions.
Composite function, yes.
Composite functions.
So xi is a function of x dash, so we can use chain rule. We are differentiating with respect to xi, but xi itself is a function of x dash j, so I can apply chain rule. Now the right side is also equal to xi I into del upon del xi, because this and this are same. Okay. So now you compare, it's a summation over j is there, as well as there is summation over I. So I and j both are dummy indices. So these components will be equal to this. Okay. So let me write down over here. So in the final step, what you have is that xi I del upon del xi is equal to xi dash j into del xi upon del x dash j into del upon del xi. Okay. So you have a linear combination of del upon del xi in the right side, as well as a linear combination of del upon del xi in the left hand side. So corresponding component must be same. So this implies that xi I is equal to xi dash j del xi upon del x dash j. Or I can rewrite it as xi dash j equal to xi I into del x dash j upon del xi. So if you are writing an expression for a vector field and you want to see how its component transform when you go from one coordinate system into another coordinate system. So this is the law of transformation for the component of a vector field when you go from one coordinates to another coordinate. Yes.
Vector field, this is the linear combination of
Del upon del xi.
yes. This is the local property of linear combination
Yes.
of vector field.
Yes. Yes.
This small vectors are saying it's a locally it's a vector. Locally what is there?
Yes.
Look, it is not a local vector field. It's a global vector field. Vector field is a global object.
This is local
But
expression.
it is only the expression when you look at its expression at a coordinate neighborhood. अगर इस कोऑर्डिनेट नेबरहुड में ये एक्सप्रेशन है तो किसी दूसरी कोऑर्डिनेट नेबरहुड में कोई दूसरा एक्सप्रेशन और वगैरह वगैरह होगा। तो जो एक्सप्रेशंस आप निकालते हैं किसी भी ऑब्जेक्ट के, वो लोकली निकाल सकते हैं क्योंकि वहीं पे कोऑर्डिनेट्स हैं। कोई ग्लोबल एक्सप्रेशन तो मैनीफोल्ड पे हो नहीं सकता, ठीक है ना, जिसमें एक्साइज आए।
अच्छा सर, मेरा एक क्वेश्चन, जैसे हमने स्मूथ मैनीफोल्ड, सी इन्फिनिटी मैनीफोल्ड लिखा है, तो यहाँ पर जो मैप जो है, जो ट्रांजिशन मैप, जो एटलस वाली एटलस के साथ, तो वो इनफाइनाइट डिफरेंशियल एंड कॉन्टिन्यूअस है, उसी सेंस में हम इसको स्मूथ मैनीफोल्ड।
यस यस एग्जैक्टली,
That's why they see it.
दैट्स राइट। Okay, so this is the law of transformation. You write down a line also. This is the law of transformation. For the component of vector field. For the components of vector field when you go from one coordinates to another coordinates। इसको मैं इस वजह से भी एम्फेसाइज कर रहा हूँ कि डिफरेंट काइंड के ऑब्जेक्ट्स हम देखेंगे मैनीफोल्ड्स पे। किसी के लॉ ऑफ ट्रांसफॉर्मेशन कुछ हैं, किसी के कुछ और तरह के हैं, तो सम टाइम वी डिस्टिंग्विश दीज ऑब्जेक्ट by their law of transformation. Okay, so these are tensorial quantities in fact. Okay, all right. Okay, next is we have some structure on the space of vector fields also. As we had a structure on the space of tangent vector, we have an algebraic structure on the space of vector fields. So, if I denote by the symbol chi m the set of all vector fields, smooth vector field, set of all smooth vector fields. वेक्टर फील्ड्स ऑन एम। अब स्मूथ मैंने पहली बार शायद ये वर्ड यूज़ किया वेक्टर फील्ड्स के लिए। अभी मैंने बताया कि वेक्टर फील्ड इज़ लोकली इज़ रिटन लाइक दिस, only locally it looks like this. In all coordinate neighborhood it will have such an expression where these i's are real valued C infinity functions. If they are C infinity functions, I will call my vector field to be a smooth vector field. If these functions are just continuous, then I will call them continuous vector field, okay, or C0 vector field. So most of the time we will be dealing with the smooth vector fields. Okay. So here is a collection of smooth vector fields on the manifold M. Okay. Now what I will do, I will define some algebraic operation on this chi m. So first of all, let me talk about the operation of addition. Can we add vector field? So the answer is yes. What we do for any pair of vector field in chi m, we define the sum x plus y, sum of two vector field as follows. I will define it as a new vector field and therefore it must operate on functions and produce functions according to the second definition. So I propose the definition as xf plus yf. Look, the right side is a function, xf is a function, yf is a function, and this sum is the sum of two functions. So when x plus y operates on a function, it gives me a function. So you can see from here that x plus y is a something which maps functions to functions. ठीक है ना? x plus y को जब हम किसी फंक्शन पे ऑपरेट करते हैं तो जो चीज़ आती है हमारे पास वो फंक्शन होती है। तो इसका मतलब ये हुआ कि इट्स ए मैप फ्रॉम हेयर टू हेयर, ऑलराइट। लेकिन अभी भी इसको आप वेक्टर फील्ड नहीं कह सकते जब तक कि आप इसको वेक्टर फील्ड साबित ना कर दें, ठीक है ना। तो इसको वेक्टर फील्ड दिखाने के लिए हमें क्या देखना पड़ेगा, क्या इसके अंदर वो दो कैरेक्टराइजिंग प्रॉपर्टी है या नहीं। यस, सो दोज प्रॉपर्टी वी हैव टू चेक। सो आवर नेक्स्ट स्टेप इज टू चेक दैट this x plus y satisfies the two properties. Number one, x plus y, when it operates on sum of two functions, it must satisfy this x plus y operating on the first plus x plus y operating on the second, ठीक है ना। और ये अभी लीनियरिटी पूरी नहीं हुई। द सेकेंड थिंग इज x प्लस वाई ऑपरेटिंग ऑन एल्फा टाइम्स f must be equal to alpha times x plus y operating on f. And the second property is when x plus y operates on the product of two functions f and g, it should satisfy Leibniz property, means x plus y operating on f into g plus f as it is x plus y operating on g. So we will check these two properties. So verification of the two properties. Let me check the first one, x plus y operating on the sum of two functions f plus g. So by the definition, this is the definition of the sum that we have proposed. So according to the definition, what should happen? X operating on f plus g plus y operating on f plus g. So now you must mention by definition. Which definition? The definition of addition in the box. Now here we know that x is a vector field. It satisfies the linear condition. So it will become xf plus xg. Same thing with y. It will satisfy linearity. So this is. Now if I take the first and the third term together, it will give me x plus y operating on f. xf plus yf is equal to x plus yf. Similarly, second and the fourth term together will give me x plus y operating on g. So you can see we have got the additivity, and similarly the second one of the linearity condition you can check. We should also try this also. So x plus y operating on f into g. So first I will apply the definition of the sum. So by that definition, x operating on f into g plus y operating on f into g. X being a vector field will satisfy Leibniz property. So you will be having xf into g as it is plus f x into x operating on g. Similarly over here, yf into g plus f times yg. Okay. So xf into g and yf into g, you write them together. So I can combine the two terms xf plus yf into g. ठीक है, आपके पास जस्टिफिकेशन होना चाहिए आपने ऐसा क्यों किया।
Sir, xf is a
ये भी एक्स एफ भी फंक्शन है, जी भी फंक्शन है, यहाँ पे भी यही मामला है, वाई एफ फंक्शन है। तो दो फंक्शंस का मल्टीप्लिकेशन और उनका एडिशन, तो डिस्ट्रीब्यूटिव प्रॉपर्टी
Can hold on this.
विल होल्ड फॉर फंक्शंस। ओके, सो अब इन दोनों को भी इसी तरह से हम कंबाइन करेंगे तो ये हमें मिलेगा एफ एक्स जी प्लस वाई जी। ठीक है ना। अब ये ब्रैकेट को देखें तो ये होगा x प्लस वाई ऑपरेटिंग ऑन f बाय डेफिनेशन ऑफ एडिशन, g एज इट इज प्लस f टाइम्स x प्लस वाई ऑपरेटिंग ऑन g. So what does it tell you? It tells you that x plus y satisfies the Leibniz property and therefore you will say, अब पूरे को सम अप कर दीजिए, and now you will conclude that x plus y is a vector field, a smooth vector field. It belongs to chi-m. तो जो डेफिनीशन सम की आपने इंट्यूटिवली लिख दी थी, उसको हमने चेक कर लिया कि इट इज़ ए प्रॉपर वैलिड डेफिनीशन ऑफ द सम. ऑलराइट, now once you have a valid definition of the sum of two vector field, you will check the nice properties of the addition. So one can check also the following properties hold. The following properties hold. This also requires verification. If I take three vector field x, y and z and you add them like this or you add them like this, you will notice that the two sums are same, and that shows that this sum which you have defined in the box satisfies the associative property. Okay, this is a matter of verification. One can easily verify. This is the first thing. The second thing is you must search out a zero vector field. So what will you propose for a zero vector field? Since vector field is a map from C infinity m to C infinity m, I define this vector field O from C infinity m to C infinity m. एक मैप मैं इस तरह से डिफाइन कर रहा हूँ और उसका नाम O या ज़ीरो whatever. So and what it does, it operates on function and gives us a zero function. सारे ज़ीरो को एक ही नोटेशन है, आपको सिर्फ कॉन्टेक्स्ट से समझना है कि ये ज़ीरो फंक्शन है या ज़ीरो वेक्टर फील्ड है या ज़ीरो टेंजेंट वेक्टर. ये कॉन्टेक्स्ट से आपको पता चल जाएगा. द ज़ीरो इन द लेफ्ट हैंड साइड इज़ ए वेक्टर फील्ड and this zero is actually a C infinity function on M. Okay. Now I have to see whether such an object is actually a vector field or not. So I must first of all check over here that it satisfies the two properties. So yes, it satisfies the linearity and it satisfies the Leibniz property. Then only you will say कि yes, it is an acceptable vector field. Okay, that can be done easily. I think these simple observations one can easily check. So we have an element 0, there exists 0 in chi-m such that, जैसे आप ये चेक कर लेंगे ये आसान हो जाएगा कि इफ़ यू ऐड इनटू एनी अदर वेक्टर फील्ड बाय दिस लॉ इट विल बी सेम एज x प्लस 0 इक्वल टू x. ठीक है, ये सारे वेरिफिकेशन आपको यहीं से करने हैं, जो स्टैंडर्ड रूल्स हैं, अपना कोई इंट्यूशन इस्तेमाल नहीं करना. ठीक है, सो दैट यस, yeah, it's a vector field and I am adding these two vector fields and this holds for all x in chi-m, and similarly the first one is true for all x, y, z in chi-m. And in the third step, you will search out a additive inverse for a given vector field, and that must behave like a minus x. So I will put its name as minus x. So given x in chi m, we define minus x as follows. I define it as a map from C infinity m to C infinity m. And it works like this: minus x operating on f equal to minus time xf. These two minuses are different. The minus in the right side is the negative of a function xf. xf अब हमारे पास एक function है, और minus f makes sense. We have defined it yesterday, okay, or earlier. And this minus x means the negative of the vector field x. इसको हम नेगेटिव अभी से कहने लगे, बट वी शुड से इट लिटिल लेटर. अब इस माइनस एक्स को जो हमने यहाँ डिफाइन किया, वेदर इट्स अ वेक्टर फील्ड और नॉट, up till now it's a map from C infinity m to C infinity m. Both the properties, characterizing properties, linearity as well as Leibniz property, वो दोनों चेक होने के बाद ही आप कहेंगे कि माइनस एक्स बिलोंग्स टू का है. तो वो दोनों प्रॉपर्टीज़ मैं छोड़ रहा हूँ एज एन एक्सरसाइज. ये वंस दीज टू आर वेरीफाइड यू विल से माइनस एक्स बिलोंग्स टू का है. और जब माइनस एक्स का एम में बिलोंग कर गया, तब आप देखेंगे कि इसके अंदर एडिटिव इन्वर्स वाली प्रॉपर्टी है कि नहीं. सो देयर फॉर ईच एक्स in chi m, there exists minus x in chi m such that what happens? Minus x plus x is 0, same as x plus minus x. तो ये एडिशन जो आपने यहाँ बॉक्स में डिफाइन किया है, दिस इज़ वेल बिहेव्ड. With respect to this addition, chi m becomes a abelian group. In the fourth step, you also see that x plus y is same as y plus x for all xy in chi m. This follows directly from the box relation, and therefore chi m is not just a set, it is an abelian group. So we conclude, after verifying all these things, that chi m under this addition is an abelian group. ठीक है. अच्छा, अभी भी नहीं रुकना, और भी ऑपरेशंस हैं वेक्टर फील्ड के ऊपर जो परफॉर्म किए जा सकते हैं. एक तो ये बाइनरी ऑपरेशन मिल गया, एक एक्सटर्नल ऑपरेशन भी है. आप वेक्टर फील्ड्स को फंक्शन से मल्टीप्लाई भी कर सकते हैं फ्रॉम द लेफ्ट. सो व्हाट आई विल डू फॉर ए फंक्शन f in C infinity m and a vector field x in chi m, we define the multiplication of x by f. We define what you call f into x. We define fx as follows. ठीक है. अब fx को मैं वेक्टर फील्ड मानना हूँ. अगर x वेक्टर फील्ड है, f कोई फंक्शन है, then fx is a vector field. So it must operate on functions. So let me operate it on a function g, और इसकी डेफिनेशन हम लिख रहे हैं f इंटू एक्स जी. ठीक है ना. तो राइट साइड में देखें, f इज़ ए फंक्शन, एक्स जी इज़ ए फंक्शन. सो दिस इनटू इज़ द ऑर्डिनरी प्रोडक्ट ऑफ टू रियल वैल्यूड फंक्शन ऑन m. तो f(x) एक ऐसी चीज़ है जो फंक्शन पे ऑपरेट करके फंक्शन प्रोड्यूस कर रहा है. तो यहाँ से ये बात तो लग गई कि दिस fx is a map from c infinity m to c infinity m. फिर हमको चेक करना पड़ेगा कि ये वाकई में वेक्टर फील्ड है या नहीं। जो कुछ भी हम लिख रहे हैं इंट्यूशन से हमें मालूम है इसका बिहेवियर क्या है, तो लिख देते हैं, लेकिन उसकी वैलिडिटी जब ही होगी जब वो दो प्रॉपर्टीज चेक हो जाएंगे। सो आई लीव वंस अगेन दीज टू थिंग्स फॉर यू टू सी वेदर एफ एक्स सेटिस्फाइज लीनियर प्रॉपर्टी, मीन्स इट मस्ट ऑपरेट ऑन g1 plus g2, two functions, and it must give me fx operating on g1 plus fx operating on g2. This one needs to check. And second also, number 2, fx operating on g1 into g2, ये लाइबनिज प्रॉपर्टी भी चेक करनी आपको पड़ेगी ज़रूर, तब जाके आप कहेंगे कि यस एफ एक्स। सो व्हाट विल फॉलो, दिस इज द सेकेंड ऑपरेशन, दिस इज बॉक्स 1, दिस इज बॉक्स 2। सो वो दोनों चीज़ें चेक करने के बाद आप लिखेंगे कि एफ एक्स बिलोंग्स टू काई एम। So it admits, the space chi m admits an external operation from the left. And then जब दो एक से ज़्यादा ऑपरेशन हो जाए तो फिर ज़रूरी हो जाता है कि उनकी आपस की compatibility चेक कर ली जाए। So now I must check these properties. Number 1, if I take two functions f and g, and I multiply a vector field x from the right with this sum, then you will see it is f into x plus g into x. ये distributive property, left distributive property, and the right distributive property should also be checked. Suppose I have sum of two vector fields and I am multiplying from the left, it is fx plus fy. ये भी चेक करने की बात है। दोनों की डेफिनेशन हमारे पास है, स्केलर मल्टीप्लिकेशन की भी और एडिशन भी, वो दोनों अप्लाई करके आप डिस्ट्रीब्यूटिव प्रॉपर्टी चेक कर सकते हैं। एंड नंबर 3, 1 into x, this one is a constant function 1, that is simply x, straightforward from here. Okay, and number 4, if you multiply two function f into g, you will get another real valued function, and this real valued function, when it multiplies with x, it gives me f into gx. This is same as g into fx. Okay. So these are the compatibility conditions. Okay, this must hold. अब ये सब प्रॉपर्टीज़ आ जाने के बाद आप क्या बोलेंगे? नहीं, वेक्टर स्पेस के लिए तो आपको स्केलर्स फील्ड से आते हैं, और ये स्पेस और जो फंक्शंस का स्पेस है ये रिंग फॉर्म करता है। सो यू आर मल्टीप्लाइंग विद द एलिमेंट्स ऑफ अ रिंग. So at this point you will say that this chi m.
So then we have to show associativity also, no, with respect to multiplication. We have shown it.
नहीं,
For ring we need associativity, that we not see here.
no, ring is the space of function. इसको मैंने रिंग नहीं दिखाया, chi m को भी रिंग नहीं बताया,
अच्छा, ये नहीं बताया सर.
इसका मल्टीप्लिकेशन थोड़ा डिफरेंट है.
Okay sir.
ये स्केलर मल्टीपल कह सकते हैं.
दो वेक्टर फील्ड का एक मतलब डॉट प्रोडक्ट एग्जिस्ट भी तो रहता है।
हाँ हाँ, इसी वजह से वो अलग,
नहीं बनता वहाँ।
हाँ इसी वजह से अलग है. So chi m with respect to this addition and scalar multiplication is a left module. अच्छा, लेफ्ट भी इम्पोर्टेंट है.
Yes.
सर लेफ्ट ही बात कर रहा है इसमें फंक्शन जो है।
अगर राइट में फंक्शन रखेंगे x के साथ, राइट में फंक्शन रख देंगे तो अब ये वेक्टर फील्ड नहीं रहा,
फंक्शन हो जाएगा।
ये फंक्शन हो जाएगा. So you can multiply a vector field from the left. So this is a left module. So this is a left module. Over what? Over ring कौन सी है इसकी? C infinity है. So space of vector field is in fact a module. But there is a multiplication also of vector fields which is defined as follows. The multiplication of vector field or the product of vector field is defined as we denote the product by the symbol bracket and we call it a Lie bracket. If there are two vector fields x and y, I will denote their product by Lie bracket xy. And if it is a vector field, once again it must operate on functions. And we propose the definition as xyf minus y xf. First you see whether this expression makes sense or not. तो पहले तो हमें देखना पड़ेगा कि राइट साइड में जो ऑब्जेक्ट है वो क्या है. yf is a function. X operating on a function is a function. Similarly, the second term is a function and the difference of two functions is a function. So the element in the right side is a C infinity function on M. So Lie bracket xy operating on a function gives me a function, means Lie bracket xy is a map from C infinity M to C infinity M. तो एक्सप्रेशन तो मीनिंगफुल था, लेकिन अभी ये देखना बाकी है कि ये वेक्टर फील्ड भी है कि नहीं. सो द आंसर इज यस. वंस अगेन वी विल चेक इट थ्रू द टू कंडीशंस. द फर्स्ट वन इज when xy operates on a sum of two functions, it must give me Lie bracket operating on f plus Lie bracket operating on g. ठीक है, तो इसको चेक कर लेते हैं हम. तो पहले तो हम ये डेफिनेशन लगाएंगे ली ब्रैकेट की. तो उस ली ब्रैकेट की डेफिनेशन के हिसाब से x y ऑपरेटिंग ऑन f प्लस g माइनस y ऑपरेटिंग ऑन x f प्लस g by the definition of Lie product. And this equals to x. Now y operating on the sum of two functions, so y being a vector field will satisfy the linear property. So it will be yf plus yg. Similarly over here xf plus xg, and this once again can be simplified. Yf is a function, yg is a function, x operating on the sum of two functions, so it must be equal to xyf plus xyg. Same thing over here, x operating on the sum of two functions means linear property. Or again here we have the same thing, yxf minus yxg. Okay, so xyf minus yxf I will write together. So this will give me xyf minus yxf. I will put it in a bracket. Similarly, second term and the fourth term will be written together. So this will give me xyg minus yxg. देखिए दिख रहा है नीचे वाली लाइन. Still like okay. So now the first bracket is nothing but Lie bracket xy operating on f. So this is xy operating on f minus, plus. This is Lie bracket xy operating on g. So you have shown that Lie bracket xy operating on f plus g equal to Lie bracket xy operating on f plus Lie bracket operating on g. So additivity holds. Similarly, homogeneity will hold on the same lines. You must check the Leibniz property also. वो भी देख लेनी चाहिए, हो सकता है उसको करने में बच्चों को दिक्कत आए. तो let us check how does it act on the product of two functions. We expect it to satisfy the Leibniz property, means Lie bracket xy operating on f, g as it is, plus f as it is, Lie bracket operating on g. This is what we are expecting. So let us start resolving it. So apply this definition written on the top. So it is x operating on y operating on f into g minus y operating on x operating on f into g. This is by definition of the Lie bracket. Second step will be x. Now y is operating on the product, so Leibniz property will hold. So by Leibniz property it will be yf into g plus f into yg. Same thing here, y operating on xf into g plus f into xg. Okay. So here in the bracket you have sum of two functions. Each function is a product of two functions. So let me simplify. So x will operate on this product yf into g plus x operating on this product f into yg.
With the linearity.
Linearity, yes. Minus y operating on xf into g and minus y operating on f into xg. अब देखिए x is operating on a product of two functions. So once again I have to appeal to
Again.
Leibniz property. So by Leibniz property it will be x operating on yf, g as it is, plus yf as it is, x operating on g. Okay. Come over here, so it will be xf into yg plus f into xyg. Okay. Same thing with this term. So y operating on xf, g as it is. Okay. And then minus xf as it is, y operating on g. एक टर्म और बचा है, वो भी आ जाएगा yf into xg and minus f into y operating on xg. अब देखिए कौन कौन से टर्म एक साथ लिखने हैं और कौन से कैंसिल हो रहे हैं. xf into yg जो है yf into xg है. So yf into xg, they will cancel each other. xf into yg कहीं है, ये भी है. They will cancel each other. अब रिमेनिंग टर्म्स को आपको प्रॉपरली लिखना है बस. x y f g और y x f कहीं है, y x f g, इनको साथ लिख लीजिए. तो डॉट जी को आप बाद में कर लीजिए. सो ये हो जाएगा एक्स वाई एफ माइनस वाई एक्स एफ इंटू जी. ये दोनों अंडरलाइन टर्म जो थे मैंने लिख लिए. अब रिमेनिंग टू टर्म्स भी है, एक प्लस एफ टाइम्स एक्स वाई जी माइनस वाई एक्स जी. अब आप दो गौर से देखिए तो आपको पता चलेगा कि द फर्स्ट ब्रैकेट इज द ली ब्रैकेट ऑफ एक्स वाई ऑपरेटिंग ऑन एफ. So this is xy operating on f, g as it is, plus f into Lie bracket xy into operating on G. So this settles the Leibniz property also. So we accept Lie bracket xy as a Lie bracket as a vector field. So product is also well defined. इतना कुछ करने के बाद आप सिर्फ ये कह सकते हैं कि Lie bracket xy belongs to chi m for all xy in chi m. Okay.
Stop.